All right, Module 6, you guys are doing great. So Module 6 is going to be about random variables. We're going to have 3 different sections in this module. And today we're going to do section 6.1. After this section, you should be able to apply the concept of discrete random variables to a variety of statistical settings, calculate and interpret the mean of a discrete random variable, calculate and interpret the standard deviation and variance of a discrete random variable, and describe continuous random variables. So, random variables, probability distribution. So we're going to have a probability model. It's going to describe all the possible outcomes of a chance process that could happen and the likelihood that those outcomes occur, the probability. So a numerical variable that describes the outcomes of a chance process is called a random variable. The probability model for a random variable is its probability distribution. So here, again, the definition: a random variable takes numerical values that describe the outcomes of some chance process, and the probability distribution of a random variable gives its possible values and their probabilities. All right, so let's consider tossing a fair coin 3 times. So what are all the things that could happen? Well, we could get tails, tails, tails. We could get heads, tails, tails. We could get heads, tails, heads. And what did I just say? Heads, tails, 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 heads, tails, telltale heads. So these are all the ones with 2 tails. And then all the ones with 2 heads. And then 3 heads as well. So here's all the different ways that we could have that. So if I wanted to make a probability distribution, so I'm just labeling x of 0 is getting all 3 tails. When it's 1, it's getting the 2 tails. When it's 2, it's getting 2 heads. And when it's 3, it's getting all 3 heads. So if I wanted to make here my, my probability distribution, I could see that 0 happened 1/8, 1 happened 3/8, 2 heads happened 3/8, and 3 heads happened 1/8 of the time. Okay, so there's my model, and now I can make a distribution over here of the model. So we could do like tossing a coin for our overall 3 times. Label your x, label your y, and here I could put it up to the 1/8, the 3/8, the 3/8, and the 1/8. And don't forget that these are all going to have equal thickness. Would this be categorical, or would this be quantitative data? All right, so in this case, we're kind of saying that this is the categorical data of just what we're getting. And then, so we could actually have these spaced out in a bar graph, but sometimes you just put them together. It's easier to see with the probabilities. Okay, discrete random variables. Remember the difference between discrete and continuous? So discrete, just kind of remembering, is a finite amount, and continuous would be an infinite amount. So we're going to have discrete random variables. So we're going to have a finite amount going on. So we're going to have discrete random variables and their probability distributions. So we could have a discrete random variable x takes a fixed set of possible values with gaps between. The probability distribution of a discrete random variable x lists the values x sub I and their probabilities. So it's just the value. We could put it here in a nice little table and their probabilities. So the probabilities, all those piece of i's, must satisfy some requirements. Probabilities can only be between 0 and 1. You can include 0 and you could include 1. in the probabilities. If 1 is included in the probability, everything else would have to be 0. Okay? Because the sum of all the probabilities is 1. It's like saying you're going to get 100% chance, which is 1. And to find the probability of an event, add the probabilities of the particular values that make up that event. Okay? So let's see some notation. If I have this guy right here, this is telling me I'm going to take the probability that x is greater than or equal to, in this case, 1. So this is the event going on. So it's the probability that whatever event x represents is greater than or equal to 1. Means, well, that's what we had. It's kind of like in algebra. Remember, if I said x is greater than or equal to, x is less than or equal to, a lot of the time you're going to see these words, at least and at most. So if I said at least, it means the least amount I could have is 2, which means I could have 2 or more. If I said at most, it means the most I could have are 2, so I could have 2 or less. All right, so let's look over this. We've got a probability distribution going on. Dr. Virginia Apgar developed a score for our babies at birth to evaluate the health of the newborns. The higher the number to 10, the healthier the baby. I want you to show that the probability distribution for X is legit. So let's look and go through. We know that all of these probabilities have to be between 0 and 1. So we're good. All probabilities are between 0 and 1 inclusively, like it could include, inclusively. Okay, so inclusively means it could include 0 or include 1. And the second thing I need to do is show that if I add all of these together, what should I get? 1. So check that in your calculator and see if that's true. So the sum of the probabilities equals 1. So we're good. Okay, B, make a histogram of the probability distribution and describe what you see. All right, so what's the biggest I'm going to go up to? 0.4. When I get to the 9. So let's see then. I am going to have the biggest I have is the 0.4. And let's see, we have the value, which goes from 1 to 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then you can label this guy the probability. And if you want to give it an overall label, I'm going to go ahead and erase this part for A, so I have a little bit more room for us. So an overall label you might put Apgar scores. Seems like a good label. All right, so let's go ahead and do our probability distribution. So 0.01, it's like barely there. 0.16, again, just barely above. 0.07, about the same. 0.08, about the same. It's really, really little going on here. Like, I probably even have mine a little too high. 0.20, 0.38, 0.099. So I'm almost to the 0.1. Mine kind of is going a little off, sorry. A little lower. And then 0.3, so I'm really jumping up here, a little over 0.3. And then at the 9, I'm going to have 0.4 above it, a little bit above. Oops. And then at the 10, I'm going to have 0.53, so I'm back down in between 0 to 0.1. So really, like, I know I have these values down here. You might want to make them so that they're right in the middle, so that you know it's just kind of talking about, oh, sorry, what was that one? That one was 0. So 0, you can't see very well. Ah, I put the eraser down the wrong spot. Okay. So like this was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 for your APGAR scores and the probability of those. So something back like that. Okay. And I actually have it drawn a little bit better, but I'll show you of me not just trying to freehand on white space, but drawing it with technology. So that was A. So there, that looks a little bit better. And again, I would give it an overall APGAR scores, maybe. An overall listing. So I think that looks a little prettier. And then what's C say? Okay, APGAR scores of 7 or higher indicate a healthy baby. So I want to find the probability that X is greater than or equal to 7. So I'm looking here, what's the probability of all of that kind of added up? So greater than or equal to 7 would be all of those. So if I add those up and find the total, that would be the probability of getting greater than or equal to 7. So I can see that that's going to be 0.908. So what does that tell us? That we have a really high probability of having a healthy baby. So about 91% or better are healthy babies. And I just looked at B. I forgot to describe what we saw. So what did we see here in B with this distribution going on? The probability distribution. Well, it's definitely going to be skewed left. And here we can see that there's a really small chance of getting an unhealthy baby. So you can see right here a very small chance. So most of them are healthy babies. And that's what we just saw going on over here when we added up 7 or above for a healthy baby. 91% is a pretty good chance you're going to have a healthy baby. And this was skewed left. Okay? Okay, NHL goals. So here is a number, another example. If you would like to try this, feel free. You can pause me, see how you do. And then when you're ready to unpause me, you can go, I'm going to advance to the next slide now, and you can see if you got them right. So the only tricky part, sorry, is making sure you know the at least wording. So make sure you're good with that. All right, so I'm going to advance. And you can see how you did. I went ahead and put it in my calculator. If you want to try to put this probability distribution in your calculator, feel free. But freehanding is just great too. I know in the calculator I don't have all the scales. Make sure you would put here goals. That's hard to see on there. Let's do maybe a red. Goals. And this would be your probability. And then overall you might put like NHL goals. And this one definitely looks skewed right. So having a lot of goals is not as likely. it looks like you can definitely are going to have four or less goals going on here. So this was 0, 1, 2, 3, 4. So I can see that more goals are going to be lower than higher. Okay, here is another one. If you're still not comfortable with everything going on, see if you could answer this. And you can pause me and unpause. So here is what I got for my answers. And hopefully you did okay. If you have any questions, let me know. And I'm going to go ahead and move on. And we're going to go to the mean of a discrete random variable. Okay, so to find the mean in that distribution, sorry, there's an announcement. Okay. I am going to have to pause this for a second.